This is the Satellite Foundation course for GOES-R training on derived motion winds, a GOES-R baseline product. Subject matter experts for this product are Jamie Daniels at NOAA and Chris Velden and co-workers at SIMS. My name is Scott and I'm guiding you through this training. Learning objectives for this module are listed on this slide. Take a look. The GOES-R derived motion wind algorithm uses 3 sequential images to estimate motion. Targets within the images are tracked, and those targets include cloud edges and water vapor gradients. 6 bands on ABI are used, and they're listed on this screen. Winds are produced in the full disk domain every hour. They're produced every 15 minutes for the CONUS domain, and they're produced every 5 minutes in the mesodomain. In this training, AHI data from Japan's Himawari 8 satellite is used as a proxy for its very close cousin ABI on GOES-R. A nested tracking technique is used to process visible, infrared, and cloudy water vapor-derived motion winds. Small 5x5 pixel sub-target scenes are nested within a larger target scene. Local motion vectors are derived for the center pixel of the 5x5 box, then this box is shifted by 1 pixel. A cluster analysis program is subsequently run to derive the dominant motion vector for the entire target scene. Finally, a height value is assigned to this dominant motion vector. The derived motion winds height assignment process requires the following GOES-R ABI cloud products: cloud mask, cloud type, cloud top pressure, and cloud top temperature. A satellite foundational course for GOES-R training for these cloud products is available. Keep in mind that any errors in the cloud height products will propagate to the height assignment process that is applied to the derived motion winds. Full details on both are in links at the end of the training. Verification statistics are derived from studies that have compared derived motion winds to co-located radiosondes, aircraft data, and model winds. The comparisons on this page are of derived motion winds for long-wave IR, visible, short-wave IR, and water vapor sources compared to aircraft data over ocean areas. The accuracy, that is the mean vector difference between the derived motion wind and the aircraft data, was between 3 and 6 meters per second, while the precision, which is the standard deviation about the mean vector difference, varied from 2.6 to 4.7 meters per second. ABI is very similar to AHI and provides a big increase in spatial resolution. In the visible from 1 kilometer to half a kilometer, and in the infrared from 4 kilometers to 2 kilometers. The temporal frequency also improves, from 15 minutes to 5 minutes or less. These improvements will result in a dramatic increase in both the aerial coverage and the accuracy of the derived motion winds. This example shows the complementary coverage provided by combining the low-level visible using the full-resolution half-kilometer imagery and the cloud-top water vapor winds for Super Typhoon Soudelor over the West Pacific. A primary use of the derived motion winds product will be assimilation into numerical weather prediction models. Many studies show that proper assimilation results in improved model forecast. One example is more accurate tropical cyclone path forecasts. This particular study from the UK Met Office shows that as more derived motion winds are assimilated, their total observational impact is increasing, resulting in better 24-hour forecasts. Derived motion winds can be used for model verification. In this case, the RUC model, the display here is of max wind speed from the RUC in cyan, underestimated the intensity of the core of an upper tropospheric jet streak over the southwestern United States. Several wind targets display velocity values of 161 to 179 knots, much higher than the 140-plus knot core that is forecast by the model. This image shows significant differences between the GFS winds in red and the Himawari 8 derived motion winds in blue. In some cases, the directional difference was as much as 180 degrees. How would this affect your interpretation of GFS model results? This example shows low-level derived motion winds from AHI were in agreement with the GFS in terms of the location of a center of a deep mid-latitude cyclone south of Kamchatka. However, east-southeast of this storm center, the derived motion winds showed a backing of winds that highlighted a region of stronger low-level warm advection that was missed by the GFS. Derived motion winds can also help diagnose mesoscale features and/or boundaries to aid in situational awareness. In this example from the Hazardous Weather Testbed blog, winds helped to verify that a favorable vertical wind profile existed ahead of a severe thunderstorm that had developed over North Texas. Low-level winds, dark blue barbs, were south to southwesterly, whereas upper-level winds, red barbs, were from the west and northwest. Here's another view of that same case over North Texas, showing the visible, infrared, and water vapor-derived motion winds computed during GOES 14 SRSOR operations. Remember that winds in GOES-R mesosectors will be produced only every 5 minutes. That's similar to the production cadence during SRSOR. Another example highlighted on the Hazardous Weather Testbed blog was a pre-frontal trough axis that was oriented from northeast to southwest across Arkansas and Texas. The visible derived motion winds added confidence in the location and movement of this boundary. How will derived motion winds be displayed in AWIPS? Low-level winds shown here are calculated for targets having a pressure of 700 millibars or greater. Vectors are computed from 3.9 micron shortwave infrared band 7 images during the night, and from 0.64 micron visible band 2 images during the day. Upper-level derived motion winds can be calculated using targets from 11.2 micron long-wave infrared band 14 images, as shown here, or by using 6.2 micron water vapor band 8 imagery. This slide should remind you what you've just learned. You can find additional information and examples about derived motion winds at the links on this slide. Click them. 2 of the HWT blog posts were referenced already in this training, but there is plenty of other information there. In addition, the ATBD, that is the Advanced Theoretical Basis document, gives all the technical information on the derived motion wind product. This concludes the Satellite Foundation course for GOES-R on derived motion winds, a GOES-R baseline product. Thanks for listening.